The night sky hides a secret that shattered our cosmic confidence. We thought we understood the universe until a single contradiction proved everything wrong. These are not just puzzles, they are profound revelations that forced scientists to rewrite the very laws of physics. You are about to explore 32 unraveled paradoxes that completely redefined our understanding of deep space. By the end, you will grasp how the cosmos truly operates, from the warping of time to the fate of everything. We will uncover why the universe is not infinite and static, and what the eerie silence of space says about our own existence. Are you ready to question the reality you think you know? A dark night sky feels perfectly natural, but it is the universe's greatest surprise. For centuries, thinkers assumed the cosmos was an endless, unchanging sea of stars. Yet in the 19th century, a German astronomer named Heinrich Olbers asked a devastatingly simple question. If the universe is truly infinite and filled with an infinite number of stars, why is the sky black? In such a cosmos, every single direction you looked, every line of sight stretching to infinity, would eventually land on the surface of a star. The entire night sky should be a single, blinding sheet of light, as brilliant as the surface of our own sun. The fact that we stand beneath a dark, star-dusted canopy means something is profoundly wrong with that ancient picture of reality. The resolution to Olbers' paradox shattered the idea of a static, eternal universe. We now understand that the universe has a finite age. Light from the most distant stars simply has not had enough time to travel across the cosmos and reach our eyes. Furthermore, the universe is not static, it is expanding. This expansion stretches the very fabric of space, causing the light from distant galaxies to lose energy and shift toward the red end of the spectrum. This cosmic redshift makes that ancient starlight dimmer and cooler, draining its intensity before it can ever illuminate our night. The profound darkness above is not an emptiness, but a beacon pointing directly to a cosmic beginning. It was a key piece of evidence that forced science to abandon an infinite, ageless cosmos and embrace the dynamic reality of the Big Bang. A simple question about the dark sky revealed that we live in a universe with a history, a birth, and a finite lifespan. And this realization about the delayed and diluted nature of starlight sets the stage for a far stranger paradox involving the messenger itself, the speed of light. That simple idea of delayed starlight rests upon a universal speed limit, the speed of light itself. Yet this cosmic rule creates a puzzle so bizarre it seems to belong in science fiction. Take a pair of identical twins. One remains comfortably on Earth, while the other boards a spacecraft capable of traveling at nearly the speed of light, heading for a distant star and then returning home. According to the common sense view of time, they should reunite having aged the same amount, but Einstein's special relativity tells a different story. The twin who journeyed among the stars would step off the ship noticeably younger than the sibling they left behind. Time itself would have passed more slowly for the traveler. This is the core of the twin paradox, and the contradiction seems stark. If all motion is relative, why is the traveling twin the one who ages less? Why isn't the situation perfectly symmetrical, with each twin viewing the other as the one moving away and thus aging slower? The resolution lies in a subtle but crucial break in symmetry. The twin on the rocket does not simply move at a constant speed. To turn around and come home, the spacecraft must slow down, reverse direction, and accelerate back towards Earth. This process of acceleration and deceleration is absolute. It is a physical experience that the traveling twin feels, a force pressing them into their seat, an experience that definitively marks their frame of reference as the one that is non-inertial or truly changing its state of motion. The earthbound twin, however, feels no such forces. They remain in a single, unchanging state of motion throughout the entire trip. This fundamental difference is the key. The laws of physics, when accounting for these periods of acceleration, consistently show that the traveling twin is the one for whom time dilates or stretches out. Their biological clocks, their heartbeats, every process within their body would proceed at a slower rate relative to the twin on Earth. This is not just a theoretical curiosity. It has been confirmed by incredibly precise experiments. Scientists have flown atomic clocks, the most accurate timekeepers ever built, on airplanes traveling at high speeds. When these clocks were compared to their stationary counterparts on the ground, they were found to be ever so slightly behind. The difference was tiny, mere fractions of a second, but it was real. High-speed travel literally slows down time. This tangible warping of time by motion is a cornerstone of modern physics, proving that time is not a universal metronome ticking at the same rate for everyone. It is a personal, relative experience deeply intertwined with how we move through the cosmos. And if mere motion can bend time, then what about the most pervasive force we know, the force of gravity itself? But if gravity can warp time itself, then the universe should be teeming with life that has had billions of years to emerge. The cosmos is unimaginably vast and ancient, containing billions of galaxies, each with billions of stars, and many of those stars likely host Earth-like planets. The numbers alone suggest that life, even intelligent life, should be commonplace. This is the very logic that led physicist Enrico Fermi to pose his famous, devastating question during a casual lunch conversation in the 1950s. So, where is everybody? The silence from the cosmos is deafening. We have pointed our most powerful telescopes and radio dishes at the heavens for decades, listening for any signal, any whisper of artificial origin, and we have heard nothing but the natural hum of the universe. This is the Fermi paradox, the stark contradiction between the high probability of extraterrestrial civilizations and the utter lack of any observable evidence for them. One compelling resolution is known as the Great Filter. This hypothesis suggests that there exists some kind of barrier, an evolutionary or technological challenge that is extraordinarily difficult for any life form to overcome. Perhaps the filter is behind us, meaning the origin of life itself was such an astronomically rare event that we are truly alone. Or, more unsettlingly, the filter may lie ahead of us. It could be that nearly all civilizations that reach our level of technological development inevitably destroy themselves, whether through nuclear war, environmental collapse, or a technology we have not yet even conceived. This would mean our own future could be far more fragile than we imagine. Other possibilities are equally profound. Advanced civilizations might be so alien that their methods of communication are utterly unrecognizable to us, like an ant trying to comprehend the internet. Or perhaps they are deliberately hiding, observing a strict policy of non-interference with developing worlds like our own. Some scientists even suggest that intelligent life might be a fleeting phenomenon, with civilizations rising and falling so quickly that the odds of two being active and close enough to communicate at the same time are vanishingly small. The Fermi paradox forces a deep and humbling introspection. It compels us to confront the possibility that we are a unique, solitary voice in a silent cosmic arena. Our search for an answer continues to drive the fields of astrobiology and the search for extraterrestrial intelligence, pushing us to redefine life and intelligence. This profound contemplation of cosmic silence leads us inward to a realm where reality itself becomes uncertain, where particles defy logic and exist in multiple places at once. That profound cosmic silence stands in stark contrast to a discovery about the universe's smallest building blocks, a discovery so strange it seems to defy the very nature of reality itself. In the 1930s, Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, pinpointed a baffling consequence of the new theory of quantum mechanics. They envisioned a pair of particles born together, becoming quantumly entangled. According to the theory, these particles would remain mysteriously linked no matter how far apart they traveled. If you were to measure a property of one particle, say its spin, you would instantly know the corresponding spin of its partner, even if that partner was on the other side of the galaxy. This instantaneous connection horrified Einstein. He called it spooky action at a distance. It seemed to blatantly violate his own theory of relativity, which established the speed of light as the universe's ultimate speed limit. Nothing, not even information, could travel faster than light. Yet here was quantum mechanics suggesting that two particles could communicate instantly, as if space between them did not exist. The EPR paradox, as it became known, presented a stark choice. Either quantum mechanics was incomplete, missing some hidden variables that predetermine the particle's states, or the universe permitted a truly spooky, non-local connection that transcended space. For decades, this remained a fierce philosophical debate. Then, in the 1980s, a physicist named Alain Aspect performed a series of brilliant experiments. He created entangled particles and measured their properties in ways that ruled out any possibility of hidden variables. The result was unequivocal. The particles were indeed instantaneously connected. Measuring one immediately influenced the state of the other, confirming the spooky action that Einstein had so deeply disliked. This was not a flaw in quantum theory, but a fundamental feature of our reality. The implications are staggering. It suggests that at a deep, fundamental level, the universe is not locally real. Objects do not have definite properties independently of being observed, and influences can indeed thread through space in a way that defies our classical intuition. This bizarre quantum link is not just a theoretical curiosity. It is the engine behind emerging technologies like quantum computing, which promises to solve problems impossible for today's supercomputers, and quantum cryptography, which could create truly unbreakable codes. The EPR paradox reveals a cosmos woven together with invisible, instantaneous threads, a universe where separation may be an illusion. And if information about a particle's state can exist in such a fragile, interconnected way, what happens to that information if the particle is utterly destroyed? This invisible quantum thread connecting particles across the cosmos faces its ultimate test at the boundary of a black hole. Here, the universe presents a conflict so profound it threatens to unravel physics itself. According to the bedrock principles of quantum mechanics, information can never be truly destroyed. You can burn a book, but in theory, if you could collect every single ash particle and trace every wisp of smoke with perfect precision, you could reconstruct the exact story that was written on its pages. The information about the book's state is merely scrambled, not erased from reality. Yet black holes, the most powerful destroyers in the universe, seem to break this sacred rule. When anything falls into a black hole, it vanishes behind the event horizon, the point of no return. According to Stephen Hawking's groundbreaking work, black holes are not completely black. They slowly leak a faint glow of radiation created by quantum fluctuations at the very edge of the event horizon. This Hawking radiation, however, is purely thermal. It is random, featureless energy, like the heat radiating from a stove. Hawking originally concluded that as the black hole emits this radiation, it loses mass and eventually evaporates completely. The terrifying implication was that all the information about what fell into the black hole, the unique properties of stars, planets, or books, would be permanently lost with it. This is the black hole information paradox, a direct war between the rules of the quantum world and the grim predictions of general relativity. For decades, physicists were stumped. How could the universe allow such a fundamental law to be broken? A potential resolution began to emerge from a startling idea called the holographic principle. This suggests that all the information describing the three-dimensional volume of a black hole is not lost inside, but is instead encoded on its two-dimensional surface, the event horizon. Imagine the information within the black hole being painted like a cosmic barcode onto its outer boundary. As Hawking radiation escapes, it is not random. It subtly interacts with this encoded data, imprinting the information about what fell in onto the escaping radiation. The information is not destroyed, it is incredibly scrambled and carried away, bit by bit, over the black hole's immense lifetime. This paradox forces a confrontation that points toward a deeper truth, a theory of quantum gravity that unites the very large with the very small. The ongoing research in string theory and loop quantum gravity treats black holes not as ultimate destroyers, but as cosmic laboratories, testing grounds for the next revolution in physics. The struggle to preserve information in the face of oblivion challenges our most basic concepts of reality, a struggle that becomes even stranger when we consider the nature of empty space itself. Even the void itself is not truly empty. According to our best theories of the quantum world, what we call empty space is a seething, frothing sea of activity. Virtual particles flicker in and out of existence, borrowing energy from the vacuum for fleeting moments before vanishing. All this frantic activity should endow every cubic centimeter of nothingness with a staggering amount of energy, a force pushing outward that physicists call vacuum energy. This energy should be the single most dominant force shaping the entire cosmos, driving an expansion of the universe so violently fast that galaxies, stars, and planets could never have formed in the first place. The math is clear and terrifying. When we calculate the expected strength of this vacuum energy, the number we get is astronomically large. Yet when we look out at the real universe and measure the actual rate of its expansion, the observed energy of the vacuum is almost zero. It is there just enough to cause the acceleration we see, but it is not just a little bit smaller than the prediction. It is 120 orders of magnitude smaller. To grasp that number, imagine writing the number 1 followed by 120 zeros. That is the size of the theoretical prediction. The observed value is like a single, solitary one, lost in an ocean of zeros. This is the vacuum catastrophe, the single worst theoretical prediction in the entire history of science. It is not a small error. It is a scream from the universe that something is fundamentally wrong with our understanding of reality. We are missing a crucial piece of the puzzle. One proposed solution is as humbling as it is controversial, the anthropic principle. This idea suggests that the cosmological constant, the term for this vacuum energy, is not a fixed number set by physics, but a random variable. In a vast multiverse of countless universes, each with different physical constants, most would have a cosmological constant so large that life becomes impossible. We, of course, find ourselves in one of the exceptionally rare universes where the value is minuscule, simply because only in such a fine-tuned place could galaxies, stars, and observers like us ever arise. It is a cosmic version of the observation that you must be alive to ask why you are alive. Other physicists find this explanation deeply unsatisfying, believing there must be a physical mechanism, a new law of nature we have not yet discovered that perfectly cancels out the vacuum energy, leaving behind the tiny residual we observe today. This paradox is a stark boundary line in modern physics. It highlights the raw incompatibility between our two most successful theories, quantum field theory and general relativity. Forcing them together on this question produces nonsense, a clear signal that we need a deeper theory, a theory of quantum gravity, to truly understand the nature of nothing itself. The vacuum catastrophe reminds us that the greatest mysteries are not always in the distant stars, but in the seemingly empty space between them. Unlocking the secret of nothing could be the key to everything, a revolution that would dwarf even the shocking discovery of what makes up most of the cosmos. Our inventory of the cosmos is missing something fundamental, the very atoms that make up our bodies and our world. When scientists tally all the normal matter, the stars, galaxies, and gas clouds we can observe, they find a shocking deficit. Roughly half of it is simply gone. This is the missing Baryon problem. Baryon is just the scientific term for ordinary matter, the protons and neutrons that form planets and people. We know precisely how much of this matter should exist from measurements of the afterglow of the Big Bang, the cosmic microwave background. That ancient light gives us a pristine invoice for the universe's initial contents. Yet when we count everything we can see in the modern cosmos, from the nearest star to the most distant quasar, the numbers do not add up. Where did 30 to 50% of all normal matter disappear to? The leading theory suggests this missing material is not in dense, shining objects, but is spread throughout the vast voids between galaxies as an incredibly hot, incredibly thin gas. This gas is so diffuse and so hot that it does not emit the kind of light our telescopes are built to see. It is essentially invisible to us, finding it required a new way of looking at the cosmos. Astronomers turn to the cosmic web, the grand architecture of the universe where galaxies are strung along immense filaments of dark matter like pearls on a string. They realized these filaments should be filled with this hidden, hot gas. Using sophisticated space telescopes that can detect the specific fingerprints of highly energized oxygen atoms, scientists have finally begun to sense this phantom material. They look at the light from distant quasars, the brilliant cores of active galaxies. As it passes through these invisible filaments, the hot gas imprints a faint, telltale absorption line on the quasar's light, a shadow that betrays its presence. This is how we are slowly accounting for the universe's missing atoms, finding them woven into the fabric of the cosmic web itself. Solving this paradox is vital. It confirms the fundamental accuracy of the Big Bang model and helps us understand the complete life cycle of matter, showing how galaxies are nourished by flows of gas from intergalactic space. It is a powerful reminder that most of the universe's ordinary matter is not in the stars, but in the dark, hot spaces between them. This successful hunt for hidden normal matter, however, only deepens a far greater mystery, one that involves a substance we cannot see at all. Finding the universe's missing atoms only makes its overall structure more puzzling. We can map the cosmic web and trace the gas between galaxies, yet this entire intricate structure rests upon a foundation of profound uniformity. Look in any direction and the cosmos looks essentially the same. This sameness is written in the oldest light we can see, the cosmic microwave background. This faint afterglow from the hot, dense infancy of the universe has an almost perfectly uniform temperature, no matter where you point a telescope. It differs by less than 0.001% across the entire sky. This presents a monumental problem. According to the standard Big Bang model, the universe simply has not existed long enough for heat to have flowed from one side to the other. The regions of space that produced the background radiation on our left and the radiation on our right were so far apart that light, and therefore any influence, could not have traveled between them in the time available. They were outside each other's cosmic horizons, completely disconnected for all of time. So how did they agree to be at the exact same temperature? It is as if you walked into a vast concert hall and found thousands of people who had never met or communicated all humming the same note in perfect pitch. This is the horizon problem, a paradox suggesting that the early universe was somehow in sync before it had time to coordinate. The most compelling solution is a theory known as cosmic inflation. It proposes that in the first sliver of a second after the Big Bang, the universe underwent a breathtaking, exponential growth spurt. Space itself expanded far faster than the speed of light, inflating a region smaller than a subatomic particle to a size larger than our entire observable universe in less than a blink of an eye. Before inflation, this tiny seed of our cosmos was small enough for every part to be in causal contact, allowing it to reach a uniform temperature, just like a single cup of coffee settles into one temperature. Then inflation took that tiny, equilibrated region and stretched it across the entire sky, locking that sameness into place on a colossal scale. The entire universe we see today was once a microscopic, connected neighborhood. This theory not only solves the horizon problem, but also explains the origin of everything. The quantum jitters that existed in that primordial seed were inflated to cosmic proportions, becoming the slight variations in density that, over billions of years, gravitationally collapsed into the galaxies and the vast cosmic web we observe today. Inflation is the pivotal event that set the stage for all of structure in the cosmos. It also left a specific imprint on the geometry of the universe, a geometry that itself holds a deep and puzzling secret. Inflation's dramatic stretching of the cosmos did more than just synchronize its temperature. It left a specific geometric signature on the universe itself. When we measure the large-scale shape of space, we find it to be incredibly flat. This is not flat like a tabletop, but flat in the geometric sense, where parallel lines remain parallel and the angles of a triangle always add up to exactly 180 degrees. Such perfect flatness, however, presents a profound puzzle. For the universe to be this flat today, its density at the moment of the Big Bang had to be fine-tuned to an unimaginable precision. The initial balance between the energy of expansion and the pull of gravity needed to be set to 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. If the universe had been even slightly denser at the beginning, gravity would have quickly won, causing everything to collapse back in a big crunch after just a few million years. If it had been slightly less dense, matter would have flown apart so rapidly that galaxies and stars could never have condensed from the cosmic soup. Our existence hinges on this razor's edge. Why was the cosmos born with such perfect, seemingly impossible balance? This is the flatness problem, a paradox of unbelievable fine-tuning. Once again, the theory of cosmic inflation provides a compelling answer. Think of the surface of a wrinkled, crumpled balloon. As you inflate it, the rubber stretches, and all those small wrinkles and curves smooth out into a much larger, flatter surface. Inflation did this to the entire universe. It took any initial curvature, no matter how warped, and stretched space so dramatically that any deviation from flatness became negligible on the scale we can observe. The universe appears flat for the same reason the ocean horizon looks flat to us, not because it is fundamentally flat everywhere, but because we are seeing only a tiny portion of an immense overall curvature. This resolution is elegant, but it carries a staggering implication. If inflation can happen, and if the initial conditions for it are random, then it might not be a one-time event. We could be living in one bubble of inflation within a vast multiverse, a cosmic froth of countless other universes, each with different physical laws and initial densities. In most of those universes, the density was not fine-tuned, and they either collapsed instantly or dissipated into nothingness. We, quite simply, could not exist anywhere else. This anthropic reasoning forces us to confront the possibility that our universe's seemingly special properties are not the result of design, but a consequence of our own existence as observers within it. The Flatness Problem reveals a cosmos balanced on a knife edge, a balance that forces us to question the very nature of reality on all scales, from the vast cosmic horizon down to the very fabric of spacetime itself. This perfect flatness stretches our understanding of reality to its breaking point, forcing us to question what is truly fundamental. Even the concept of a vacuum, the very definition of empty space, is not as solid as it seems. Picture an astronaut floating in the void, completely at rest. They feel the cold of space and detect nothing but emptiness around them. Now, imagine another astronaut in the exact same patch of cosmos, but this one is strapped into a rocket, accelerating at a tremendous rate. According to quantum field theory, this second astronaut would not experience a cold vacuum. They would instead feel a warm glow, and their instruments would detect a bath of particles. This is the Unruh Effect, a paradox where two observers in the same location disagree completely on the most basic facts of their environment. One sees a true void, the other sees a warm sea of real particles. The resolution lies in the bizarre, observer-dependent nature of reality in the quantum world. Particles are not simply little balls that exist independently. They are better understood as excitations or ripples in underlying quantum fields that fill all of space. For the accelerating astronaut, their frantic motion through these fields creates a kind of friction or disturbance. This interaction excites the fields, causing ripples that appear to them as real, detectable particles with a specific temperature. The astronaut at rest, moving smoothly through the cosmos, simply does not create these ripples, and so perceives only the calm, unexcited field. There is no single, objective answer to the question, what particles are here? The answer depends entirely on your state of motion. This profound link between acceleration and heat provides a crucial clue to one of the universe's greatest mysteries. The mathematics of the Unruh effect is nearly identical to that of Hawking radiation from black holes. In both cases, an event horizon is key. For the accelerating astronaut, there is a point in space they can never receive signals from, a horizon created by their own motion. For a black hole, it is the event horizon from which nothing can escape. In each scenario, the horizon distorts the quantum fields, forcing them to produce radiation. This deep connection suggests that gravity itself may not be a fundamental force, but rather a consequence of the universe's thermodynamics, a kind of heat and entropy associated with spacetime itself. The Unruh effect shatters our classical intuition, revealing a cosmos where existence is not an absolute, but a relationship between the observer and the fabric of reality. If even the particles that make up our world are not fundamental, but dependent on our own motion, then what does that say about the ultimate nature of the cosmos we call home? If even the particles we are made of depend on our motion, then our very consciousness might be an illusion. This line of thought leads to one of the most unsettling ideas in all of cosmology, the Boltzmann brain paradox. Imagine the universe existing for an eternity, or perhaps undergoing endless cycles of death and rebirth. In such an infinite span of time, the random jostling of atoms dictated by the laws of probability makes every conceivable event not just possible but inevitable. Given enough time, a fully formed, self-aware brain could spontaneously assemble from the chaos, complete with a lifetime of fabricated memories, thinking it is a person living in a real world. The statistics are terrifying. In an eternal cosmos, these isolated, disembodied minds would be vastly more common than the slow, orderly evolution of an entire universe filled with galaxies, planets, and billions of genuine beings. The odds overwhelmingly favor you being a lone Boltzmann brain, having just popped into existence a moment ago with the false memory of reading this sentence, rather than a product of 14 billion years of cosmic evolution. This is not just a philosophical curiosity, it is a direct threat to science itself. If we cannot trust that our memories and observations of a consistent, ancient universe are real, then all of our scientific inferences, from the Big Bang to evolution, become meaningless. We could be nothing more than fleeting accidents in a mindless void. This paradox forces physicists to impose boundaries on our cosmological models. An eternally inflating multiverse or a cyclical cosmos that produces infinite Boltzmann brains is, by this logic, empirically unsupportable. To resolve the paradox, we must either accept that the universe had a definite beginning and will have a definite end, preventing an infinite timeline, or we must appeal once more to the anthropic principle. Perhaps we do not observe ourselves as Boltzmann brains for the simple reason that a conscious experience rooted in a stable, ordered universe is a prerequisite for making the observation at all. A fleeting brain would vanish before it could form a coherent thought. The Boltzmann brain paradox takes us to the precipice of metaphysics, forcing us to question the reliability of everything we think we know. It suggests that the ultimate foundation of reality may not be matter or energy, but stable, consistent information. That unsettling possibility of a fleeting consciousness brings us to a paradox burning at the very edge of a black hole. The event horizon should be an invisible boundary, a point of no return that feels like nothing at all to someone falling through. Einstein's equivalence principle assures us that a freely falling astronaut would experience pure weightlessness, unaware of their doom until the immense tidal forces far inside tore them apart. But when we apply the rules of quantum mechanics to this scenario, a terrifying alternative emerges. The horizon might not be a silent gateway. It could be a blazing firewall, an annihilating curtain of ultra-high-energy particles that would instantly vaporize anything attempting to cross. We are left with two completely different realities dictated by our two most successful theories. General relativity promises a smooth, uneventful passage. Quantum mechanics predicts a violent, cosmic execution. This is the black hole firewall paradox, and it represents a direct and dramatic clash between the pillars of modern physics. The conflict arises from a careful study of quantum entanglement near the horizon. To preserve the fundamental principle that information cannot be lost, a complex transfer of entanglement must occur between the radiation leaving the black hole and the particles just inside the event horizon. This necessary transfer, according to the math, seems to break the entanglement between particle pairs straddling the horizon. That severing of quantum links releases a catastrophic amount of energy, manifesting as the firewall. One potential resolution is that these destructive walls only form under very specific conditions, perhaps in older black holes. Another, more radical idea is that our entire understanding of quantum entanglement and locality is flawed, requiring a complete overhaul of how we view spacetime itself. The firewall dilemma is more than a theoretical puzzle. It is a screaming signal that our picture of reality is fundamentally incomplete where gravity and quantum mechanics meet. The intense debate it sparks drives physicists to explore the wild frontiers of string theory and loop quantum gravity, searching for the missing key that will unite these warring descriptions of our universe. This fiery conflict at the precipice of oblivion forces us to look beyond individual black holes and confront a mystery affecting the entire cosmos. This fiery conflict at the precipice of oblivion forces us to look beyond individual black holes and confront a mystery affecting the entire cosmos. Even as we struggle to understand the edges of black holes, a different crisis is unfolding across the vast, expanding universe. We call it the Hubble Tension, and it is a discrepancy so stubborn it threatens to crack the foundations of modern cosmology. For nearly a century, we have known the universe is expanding, with galaxies flying away from each other at a speed described by the Hubble constant. The problem is, we have two supremely confident ways to measure this speed, and they are giving us different answers. One method uses the cosmic distance ladder, a meticulous chain of measurements that builds from nearby stars to distant galaxies. Astronomers use pulsating stars called Cepheid variables and cataclysmic stellar explosions known as Type 1, a supernova, as standard candles, objects with a known intrinsic brightness. By observing how dim they appear, we can calculate their distance and, in turn, the universe's expansion rate. This approach yields a specific, robust number. The other method looks back to the very beginning. It analyzes the cosmic microwave background, the faint afterglow of the Big Bang, using the exquisite data from the Planck satellite. This ancient light gives us a snapshot of the infant universe, and by applying our standard model of cosmology, we can predict how fast the universe should be expanding today. This prediction gives us a different number for the Hubble constant. The two results disagree by a small but definitive amount. This is not a minor statistical fluke. It is a growing tension, a persistent gap that has only become more certain as our measurements have grown more precise. One path, looking at the local, modern universe, tells us it is expanding faster than the other path, which reads the primordial blueprint, says it should be. This contradiction suggests that our standard cosmological model, the lambda cold dark matter model, might be missing a crucial ingredient, perhaps dark energy, the mysterious force driving cosmic acceleration, is not constant as we have assumed. Maybe it is evolving, growing stronger over time, pushing galaxies apart more aggressively than our models allow. Alternatively, there could be unknown types of relativistic particles, often called dark radiation, flooding the early universe and altering its expansion history. The possibility of new physics is both thrilling and daunting. For years, astronomers have subjected both measurement techniques to intense scrutiny, searching for a hidden systematic error, a flaw in our methods that could explain the difference. Perhaps our understanding of Cepheid variables is subtly wrong, or maybe our map of the cosmic microwave background holds an unaccounted-for anomaly. Yet, despite this exhaustive re-examination, the tension refuses to go away. This paradox is a powerful reminder that cosmology is driven by empirical evidence. Even our most well-established constants are not immune to mystery. The concerted effort to resolve the Hubble tension is now a central goal of astronomy, driving the development of powerful new tools like the James Webb Space Telescope and ambitious sky surveys. They are not just making better measurements, they are hunting for clues to a deeper cosmic truth. The challenge of pinning down the universe's expansion rate forces us to look more closely at the very engine of that expansion, the enigmatic force we call dark energy. This stubborn tension in the expansion rate forces us to confront a problem that makes the Hubble disagreement look like a minor accounting error. The energy of empty space should be the most powerful force in the cosmos, yet it is almost nothing. We have already touched upon the staggering mismatch between the vacuum energy predicted by quantum theory and the tiny value we actually observe, a discrepancy of 120 orders of magnitude. This is the cosmological constant problem in its rawest form. To call it the worst prediction in the history of science is not an exaggeration. It is a scream from the data that our most fundamental ideas about reality are broken. Quantum field theory tells us that the vacuum is a seething foam of virtual particles, and all that frantic activity should fill every cubic centimeter of nothingness with an immense, repulsive energy. If that were true, this energy would have ripped the universe apart in its first moments, preventing anything from atoms to galaxies from ever forming. Yet here we are, in a universe where the cosmological constant is not just a little smaller, but is a decimal point followed by 120 zeros, and then a tiny number. This is not a small error, it is a chasm of ignorance. One proposed solution is as humbling as it is controversial. Perhaps the cosmological constant is not a fundamental constant set by physics, but a random variable. In a vast multiverse, a cosmic landscape of countless universes bubbling into existence, each one has a different value for this vacuum energy. In the overwhelming majority, the value is enormous, and those universes expand so violently that no structure can ever form. We, of course, find ourselves in one of the exceptionally rare universes where the cosmological constant is minuscule, simply because only in such a placid cosmos can galaxies, stars, and curious observers ever arise. This anthropic reasoning offers an explanation, but it feels to many like a surrender, an admission that we cannot find a deeper physical law. The alternative is to search for that law. Perhaps a profound, yet undiscovered symmetry in nature forces the vacuum energy to cancel itself out almost perfectly, leaving behind only the faint whisper we detect as dark energy. Or maybe dark energy is not a constant at all. This idea leads to the concept of quintessence, a dynamic field that permeates space and changes slowly over time. Unlike a true cosmological constant, quintessence could have been different in the past and may evolve in the future. This could potentially help explain the Hubble tension, as a slowly strengthening quintessence field would mimic a higher expansion rate today. Yet even quintessence models struggle to explain the incredible smallness of the vacuum energy we observe. The cosmological constant problem is more than a puzzle. It is a direct challenge, a stark reminder that we do not understand the nature of nothing. It underscores the raw incompatibility between quantum mechanics and general relativity, forcing a confrontation that can only be resolved by a theory of quantum gravity. Unlocking the secret of why empty space weighs almost nothing could be the final key to a unified theory of physics. This profound ignorance about the vacuum forces us to ask what happens when we apply quantum rules not to particles or fields, but to the entire cosmos. Our struggle to define the vacuum's energy leads to a deeper, more abstract paradox, one that challenges time itself. In the quest to merge general relativity with quantum mechanics, physicists John Wheeler and Wheeler-DeWitt formulated a groundbreaking equation meant to describe the entire universe in quantum terms. This Wheeler-DeWitt equation is the ultimate expression of quantum cosmology, a mathematical recipe for the wave function of the cosmos, yet it contains a shocking omission. The variable for time is completely absent from its core. According to this fundamental description of reality, the universe at its most basic level does not evolve or change. It simply is. The entire cosmos, from the Big Bang to the distant future, is frozen into a single, static block. This presents a devastating contradiction. Our entire existence is defined by the relentless, irreversible flow of time. We feel it in our heartbeat, we see it in the aging of stars, and we build our lives around its passage. How can this vivid, undeniable experience of past, present, and future emerge from a bedrock reality that is fundamentally timeless? The equation suggests that time is not a fundamental ingredient of the universe, but an emergent property, a collective illusion that arises from the complex interactions within the system, much like the temperature of a gas emerges from the frantic motion of countless individual molecules. A single molecule does not have a temperature, only a vast ensemble of them does. In the same way, perhaps time is a property that only manifests for beings like us, embedded within the universe and interacting with its countless parts. We are like readers immersed in a novel, experiencing the story linearly, page by page, while the book itself, the complete object, exists all at once. Resolving this paradox is a central goal of quantum cosmology. It forces physicists to understand how classical time and causality, the clear chain of cause and effect we rely on, can bubble up from an underlying quantum substrate that knows no such order. This touches upon the deepest questions of consciousness and perception. Is our experience of time a necessary artifact of being a complex, information processing system within a much larger, timeless whole? The Wheeler-DeWitt Equation pushes us to the precipice of philosophy, questioning whether time is a feature of the world or a construct of the mind. This radical rethinking of time's nature makes the apparent coordination of the cosmos seem even more miraculous. If the universe is a timeless static block, then the conditions that allow for life were not just set in the distant past, but are woven into the entire frozen structure, a perfect and permanent fine-tuning from the very beginning. This timeless, frozen cosmos described by the Wheeler-DeWitt Equation is built upon a set of rules so precise it defies belief. The fundamental constants of nature, the very numbers that govern the strength of forces and the masses of particles, appear to be exquisitely fine-tuned for life. Consider the force of gravity. If it were even slightly stronger, the universe would have collapsed back on itself in a fiery big crunch long before stars could form. If it were slightly weaker, matter would have flown apart so rapidly that galaxies never could have coalesced from the primordial soup. The same razor's edge balance applies to the strong nuclear force that binds atomic nuclei. A change of just 1% in its strength would have prevented the formation of carbon, the essential building block of life as we know it, leaving the universe filled with only hydrogen and helium. Even the initial expansion speed of the universe, as revealed by the Flatness Problem, was calibrated to an unimaginable precision of 1 part in 10 to the power of 60. Why does our universe possess this seemingly miraculous set of numbers that allows for complexity, planets, and observers? This is the fine-tuning problem, and it forces us to confront the deepest questions of existence. Is this perfection a mere cosmic accident? One compelling answer is the anthropic principle. In its simplest form, it states that we observe a universe compatible with life for the one undeniable reason that we are here to observe it. If the constants were any different, we would not exist to ponder the question. This reasoning finds a powerful home in the multiverse theory. If our cosmos is just one bubble in an infinite froth of universes, each with its own random set of physical laws, then it is no surprise that we find ourselves in one of the rare, hospitable ones. In most universes, the constants are wrong, and those realms remain dark, empty, and lifeless. Another possibility is that the fine-tuning is not random at all, but necessary. Perhaps a deeper, yet-to-be-discovered theory of everything will reveal that these constants are not free parameters, but are mathematically locked into place, the only possible outcome from a single, elegant equation. For some, the apparent design points toward a transcendent cause, a cosmic architect who set the dials. The fine-tuning problem sits at the volatile intersection of physics, philosophy, and theology, a paradox that refuses a simple answer. It challenges our concepts of chance and necessity, leaving us to wonder if our universe is a stunningly unlikely coincidence, an inevitable outcome, or something else entirely. This profound contemplation of a cosmos tailored for awareness makes the relentless, one-way flow of time we experience feel all the more personal and poignant. This relentless fine-tuning for life exists within a universe where time flows in only one direction. We remember the past but not the future. A shattered glass never reassembles itself. This one-way street of cause and effect is so fundamental to our existence that we rarely question it. Yet the fundamental laws of physics, the equations governing particles and forces, are almost perfectly time-symmetric. They work just as well running forward as they do in reverse. There is nothing in Newton's laws or quantum mechanics that forbids a scattered pile of glass shards from spontaneously jumping up to form a whole cup on a table. So why do we never see it happen? This is the arrow of time paradox, the profound disconnect between the reversible nature of microscopic laws and the irreversible flow of our everyday experience. The answer lies in a concept called entropy, which is essentially a measure of disorder or randomness. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. A tidy room tends toward mess, a hot coffee cools to room temperature, and a star radiates its heat into the cold void. These processes are not reversible because they represent a move from a state of low entropy or high order to a state of high entropy or maximum disorder. The arrow of time is the direction in which entropy increases, but this just pushes the mystery one step back. Why was the entropy of the universe so incredibly low in the first place? The Big Bang represents the most ordered, low-entropy state our cosmos has ever known. All the matter and energy of the entire universe was crammed into an ultra-hot, ultra-dense, but remarkably smooth and uniform speck. This is the ultimate cosmic puzzle. Why did the universe start with such a special, pristine configuration? A wound-up spring that has been unraveling ever since, giving us the past, the present, and the future. Some physicists propose a past hypothesis, a postulate that the universe simply began in this low-entropy state as a brute fact of nature. Others look to cosmological models like inflation, which naturally explains how a tiny, quantum-scale patch could be smoothed out and stretched into our vast, orderly beginning. The arrow of time connects the fate of the entire cosmos to our most personal experiences. Our ability to make memories, our sense of free will, even the very process of consciousness may be tied to this irreversible increase in cosmic disorder. We are creatures of the second law, our lives defined by the one-way journey from order to chaos. This irreversible current makes the possibility of a cosmic mirror, a reality where time runs backward, seem like pure fantasy. The irreversible flow of time feels absolute, a one-way river carrying us from birth to death. Yet hidden within Albert Einstein's equations of general relativity are solutions that twist this river into a loop. Certain configurations of matter and energy, like a hypothetical infinitely long cylinder spinning at nearly the speed of light, known as a Tipler cylinder, could warp spacetime so severely that it creates a closed time-like curve. This is a path through the cosmos that circles back on itself, allowing an object to travel into its own past without ever exceeding the speed of light. You could theoretically follow this curve and arrive at the same event from which you departed, meeting your former self. This mathematical possibility shatters our intuitive understanding of cause and effect, leading directly to the infamous grandfather paradox. Imagine a traveler using such a loop to go back in time and prevent their own grandfather from meeting their grandmother. If successful, the time traveler would never be born, rendering the journey itself impossible. So who prevented the meeting? The paradox creates a logical inconsistency that seems to forbid such backward travel. most physicists argue that these exotic solutions are not physically possible. The energy required to create a Tipler cylinder is beyond any conceivable technology, and many believe quantum effects would inevitably disrupt the formation of a stable time loop, protecting the sanctity of causality. Yet these hypothetical constructs are far from useless. They serve as ultimate thought experiments, stress-testing the fabric of general relativity and forcing a deeper consideration of determinism. If time travel to the past were possible, would the universe simply not allow any action that creates a paradox, enforcing a single, self-consistent timeline where your attempt to change history was always part of what happened? Or does every potential intervention branch reality into a new, parallel universe? More profoundly, the potential for time travel introduces a cosmic-scale information paradox. If you can send a message into the past, where did that information originally come from? It appears from nowhere, violating fundamental conservation laws. These dizzying possibilities, born from the pure language of mathematics, highlight the stark boundary between what is theoretically possible within our equations and what is physically plausible in our universe. They remind us that time itself may be far more flexible and strange than our everyday experience suggests. This bizarre power of observation to alter reality is not confined to the microscopic world. A watched quantum pot never boils. This is the essence of the quantum Zeno effect, a phenomenon where the simple act of repeatedly measuring a system can freeze it in its initial state, preventing its natural evolution. The effect draws its name from the ancient Greek philosopher Zeno, who argued that a flying arrow is motionless because at any single instant it occupies a specific space. In the quantum realm, a version of this paradox becomes real. Imagine a single, unstable atom poised to decay. Left unobserved, its quantum wave function will evolve, and it will eventually split apart. But if you bombard this atom with a rapid, continuous series of measurements, constantly asking, "Have you decayed yet?" the relentless observation resets the system's internal clock. The atom, perpetually caught in the act of being measured, never finds the uninterrupted time to make the transition. It is trapped by the gaze of the observer. This is not just a philosophical idea. It has been demonstrated in laboratories using lasers to repeatedly probe the state of atoms and ions, effectively stopping their quantum evolution in its tracks. The practical implications are profound. In the race to build quantum computers, scientists use this principle to protect fragile quantum bits, or qubits, from decoherence. By frequently but gently checking their state, they can prolong the qubit's useful life, fighting back against the natural tendency of quantum information to dissolve into noise. This forces a deep philosophical confrontation. Does consciousness itself play a role in collapsing the wave function, or is it simply the physical interaction of the measuring device that causes the freeze? The quantum Zeno effect blurs the line between the observer and the observed, suggesting that at its most fundamental level, reality requires a certain amount of privacy to unfold. To change, a system must be left alone. This leads to an even more profound question about the cosmos. If our observations can alter the behavior of tiny particles, could the universe itself be understood as a vast, ongoing computation whose very laws are a form of information processing? Jacob Bekenstein made a startling proposal. A black hole, the ultimate symbol of disorder and chaos, must itself possess entropy. This was a radical leap. Entropy measures the number of ways a system's internal components can be rearranged without changing its overall appearance, a count of its hidden disorder. For a box of gas, the entropy is proportional to its volume because the more space inside, the more ways the molecules can be arranged. but a black hole, according to classical general relativity, is featureless. It has no hair, no internal parts to rearrange. It is defined only by its mass, spin, and charge. So where could its immense entropy possibly reside? Wittgenstein and later Stephen Hawking found the answer not within the black hole's volume, but on its boundary. A black hole's entropy is exactly proportional to the area of its event horizon. This discovery was paradoxical. It meant that all the information about everything that ever fell into the black hole, every star, every planet, every book, was not lost in the three-dimensional depth. Instead, it was encoded on the two-dimensional surface of the horizon, like a cosmic DVD storing a three-dimensional movie. This is the holographic principle, a concept that turns our intuition about space inside out. We naturally assume that a container's information capacity depends on its volume. Yet for the most powerful container in the universe, the capacity is set by its surface area. It is as if the entire three-dimensional world we experience, with its depth and substance, is a projection, a hologram emanating from a vast, thin, two-dimensional surface at the edge of the cosmos. This resolves the information paradox in a breathtaking way. Information is not destroyed when it crosses the event horizon. It is smeared and stored across the horizon's surface, and it is slowly radiated back out, scrambled into Hawking radiation over eons. The black hole entropy paradox is a crucial clue in the quest for quantum gravity. It tells us that space-time itself may not be fundamental. The smooth, continuous fabric of the universe could be an emergent property, a collective behavior of countless microscopic bits of information living on a distant, lower dimensional boundary. This holographic idea has become a guiding light in theoretical physics, suggesting that the universe is a kind of computation, a vast translation of data from one dimension to another. If even light must travel through this holographic reality, how does its fundamental nature hold up under such a radical reinterpretation? The holographic principle redefines reality, but its implications shake the very foundations of gravity. For over a century, Einstein's equivalence principle has stood as a cornerstone of general relativity. It states, with elegant simplicity, that the force you feel in an accelerating rocket is fundamentally the same as the force of gravity pulling you to the ground. There is no experiment you could perform inside a closed, windowless laboratory that could distinguish between the two. This principle of equivalence is so foundational that physicist Leonard Skiff conjectured it must be true. He argued that any complete and self-consistent theory of gravity would be forced to incorporate it. It is not merely a happy coincidence, but a necessary feature of our universe. Yet this bedrock certainty faces a direct challenge from the quantum realm. In the bizarre world of quantum field theory, the vacuum is not empty. It is a vibrant sea of virtual particles that flash in and out of existence. When you place an object in this quantum sea, its very presence can alter the energy of the vacuum around it. This creates a subtle, quantum-induced force. Crucially, this force can depend on an object's internal composition, on the specific particles that make it up. This presents a profound problem. The equivalence principle insists that all objects, regardless of their makeup, fall at the same rate in a gravitational field. But if the quantum vacuum exerts different forces on different materials, could a block of iron and a block of wood fall at slightly different speeds? The principle might be violated by these tiny quantum effects. For decades, scientists have tested this with incredible precision. They have dropped objects in evacuated towers and even used entire moons as test masses in orbital experiments. So far, no deviation has been found. The equivalence principle holds firm, a testament to Einstein's genius, but this very steadfastness deepens the mystery. If the quantum vacuum is real and active, why does it not disrupt this perfect equivalence? The search for a crack in this foundation is a search for new physics. A confirmed violation would be a monumental discovery, pointing directly toward the need for theories like string theory or loop quantum gravity, which attempt to weave gravity and quantum mechanics into a single fabric. The silence from these experiments is both a confirmation of Einstein's insight and a puzzle. It suggests that the universe possesses a deeper symmetry, a hidden mechanism that protects the equivalence principle from the quantum chaos. This relentless testing of gravity's most basic rule forces us to confront the most glaring omission in our cosmic inventory, the universe's missing mass. Our most precise tests of gravity confirm its perfect consistency, yet this same force reveals a ghost haunting the cosmos. When astronomers measure how fast stars orbit the centers of galaxies, they find something deeply unsettling. According to the laws of gravity, stars on the outer edges of a spiral galaxy, far from the central mass, should move slower than those closer in, just as Pluto orbits our Sun more sluggishly than Earth. But observation after observation reveals the opposite. These distant stars whip around at nearly the same high speed as their inner neighbors. It is as if the entire galaxy is embedded within an immense, invisible sphere of mass, a halo of something that does not emit or absorb any light. We see its gravitational pull, but we cannot see the source. This is the dark matter paradigm. The evidence does not stop there. Giant clusters of galaxies act as cosmic lenses, warping the fabric of space-time so severely that they bend the light from objects behind them, creating distorted arcs and multiple images. The amount of bending is far too great to be caused by the visible stars and gas alone. There must be 6 times more invisible matter than visible matter holding these cosmic structures together. For decades, the leading hypothesis has pointed to an exotic particle, a weakly interacting massive particle, or WIMP. This particle would be a relic from the Big Bang, passing through our planet like a ghost through a wall. Yet every attempt to catch one of these phantoms has failed. Deep underground, in mines and tunnels shielded from cosmic rays, exquisitely sensitive detectors have waited for the faintest bump of a WIMP collision. They have heard nothing but silence. This is the core of the paradox. The gravitational evidence for dark matter is overwhelming, but the particle itself remains utterly elusive. If it is a WIMP, why is it so shy? Alternative candidates have emerged, from strange particles called actions to a cosmic swarm of primordial black holes formed in the universe's first second. But like the WIMP, none have been confirmed. The continued failure to find a particle has led some physicists to propose a radical alternative. Perhaps we are not missing matter, but are instead misunderstanding gravity. The theory of modified Newtonian dynamics, or MUND, suggests that gravity behaves differently at the extremely low accelerations found in the outskirts of galaxies. It can reproduce those flat rotation curves without any invisible matter, but MUND faces its own severe challenges. It struggles to explain the precise gravitational lensing we see from galaxy clusters without adding some form of dark matter anyway. The Bullet Cluster, a cosmic collision of 2 galaxies, provides a particularly sharp rebuttal. The visible gas from the collision was slowed and stuck in the middle, but the gravitational lensing effect shows that most of the mass sailed right through, clearly separated from the normal matter. This suggests a form of matter that does not interact with anything except through gravity. Dark matter is the ghost in the cosmic machine, an unseen architect that sculpted the galaxies and the cosmic web. Its resolution demands a revolution, either in our particle detectors or in our fundamental laws of physics. This search for the universe's missing mass is a race to understand the invisible framework of reality, a quest that runs in parallel with the mystery of the void's own accelerating push. That ghostly dark matter is not the only invisible force shaping our cosmic fate. The true master of the universe's destiny is something even more baffling, a pressure in the vacuum of space itself. In the late 1990s, two independent teams of astronomers made a discovery that would shatter our cosmic expectations. They were observing distant stellar explosions, Type 1, a supernova, to measure how much the universe's expansion had slowed over time. Every scientist was certain that the collective gravity of all matter would be putting the brakes on the cosmos. Instead, they found the opposite. The most distant supernova were fainter than they should have been, meaning they were farther away than anyone had predicted. The expansion of the universe was not slowing down, it was speeding up. This was the stunning revelation of dark energy, a repulsive force that now dominates the universe's energy budget. Its nature is the single greatest mystery in modern cosmology. Is dark energy simply the cosmological constant, a fixed property of empty space as Einstein once proposed? Or is it something dynamic and changing, a cosmic field that physicists call quintessence? This field could evolve over time, potentially weakening or strengthening, altering the universe's ultimate fate. Other theories are even more radical, suggesting that Einstein's theory of general relativity itself breaks down on the largest cosmic scales. Perhaps what we perceive as dark energy is merely a shadow, a sign that our understanding of gravity is incomplete and needs modification. Some physicists look to the possibilities of string theory, proposing that the influence of extra dimensions we cannot perceive could be leaking into our universe, manifesting as this accelerated expansion. The stakes for this enigma could not be higher. The nature of dark energy dictates the final chapter of everything. If it is a true cosmological constant, the universe will continue expanding at an ever-increasing rate, eventually tearing apart galaxy clusters, solar systems, and even the fabric of spacetime itself in a final event known as the Big Rip. If it is quintessence, it could one day decay away or even reverse sign, pulling the universe back together in a catastrophic Big Crunch. To solve this, astronomers are developing powerful new observational probes. The Vera C. Rubin Observatory will map billions of galaxies, while the Nancy Grace Roman Space Telescope will peer back in time, charting the expansion history of the universe with unprecedented precision. They are hunting for the slightest wiggle in the growth of cosmic structures, a tiny clue that could reveal whether dark energy is constant or dynamic. This profound challenge to our standard model forces physics to look beyond its established boundaries, to consider realities where connections defy the very concept of distance. This deep interconnectedness defies our most basic assumptions about space. Einstein derided it as spooky action at a distance, a ghostly link that seemed to break his cosmic speed limit. But was it real? For decades, it remained a philosophical debate until a physicist named John Bell devised a mathematical test. His theorem provided a clear, experimental way to distinguish between a universe with hidden local variables and one with true, inherent spookiness. The test involved measuring the properties of entangled particles, like their spins, in different directions. If local hidden variables existed, the correlations between these measurements would never exceed a certain limit. If quantum mechanics was correct and the connection was truly instantaneous and non-local, the correlations would violate that limit. The experiments that followed, beginning with Elaine aspects in the 1980s, were unequivocal. They showed again and again that the quantum predictions were right. The correlations between the entangled particles were stronger than any local, hidden variable theory could ever explain. Influences between them were not traveling through space, they were simply ignoring it. This is the heart of quantum non-locality, a paradox where two particles light-years apart behave as a single entity. The universe, at its most fundamental level, is not a collection of separate things but a deeply woven whole. Yet this faster-than-light connection does not allow you to send a message. The outcome of your measurement on one particle is random. You cannot control whether you find spin up or spin down. It is only by comparing your random result with the random result from the other side, long after the fact, that you see the perfect, spooky correlation. Because you cannot force a specific outcome, you cannot encode information into the instantaneous link. The cosmic speed limit for sending a signal, for transmitting a bit of usable data, remains unbroken. Relativity is saved, but our classical intuition is left in ruins. We are forced to accept that the universe is fundamentally non-local. This is not a flaw in quantum theory, but one of its defining features. And this very strangeness is now being harnessed. Quantum cryptography uses this entangled link to create perfectly secure codes. Any attempt to eavesdrop on the transmission inevitably disturbs the delicate quantum connection, alerting the users to the intrusion. Quantum computers leverage the interconnected states of many qubits to perform calculations that would take conventional supercomputers millennia. The paradox of non-locality has moved from a philosophical curiosity to an engineering principle, proving that the universe's deepest mysteries can become its most powerful tools. This profound quantum link, where distance is an illusion, prepares us to examine connectivity on the grandest scale of all, the architecture of the entire cosmos. That deep quantum interconnectedness seems to find a mirror in the largest structures we can see. For generations, a bedrock assumption of cosmology has been the cosmological principle, the idea that on the grandest scales, the universe is homogeneous and isotropic. This means it should look roughly the same in every direction and from every point, a vast, evenly distributed cosmic soup. But our telescopes are now revealing features that strain this elegant simplicity to its breaking point. We have found colossal formations like the Hercules Corona Borealis Great Wall, an immense filament of galaxies so large it would take light 10 billion years to travel from one end to the other. This is not just a big structure, it is a theoretical impossibility within our standard model. Such enormous features should not have had enough time to form through gravity alone since the Big Bang. Their sheer scale challenges the very definition of homogeneity, forcing us to ask, at what point does the universe truly become smooth? Is our cosmic horizon simply not large enough to see the true average? Or are we witnessing a fundamental flaw in our understanding? The existence of these giant walls and voids suggests the early universe might have had seeds of structure far greater than our models predict, perhaps planted by unknown physics in the first moments of inflation. Resolving this paradox is a driving goal for the next generation of sky surveys, which will map millions of galaxies in unprecedented detail. They are not just making a bigger map, they are testing a foundational pillar of modern cosmology. If the cosmological principle falters, it would force a radical rewrite of our cosmic story, challenging the uniformity that has guided our theories for a century. This questioning of a single, uniform beginning naturally leads us to wonder if the cosmos itself is capable of repetition, of death and rebirth on a scale beyond our comprehension. The idea of a universe with multiple beginnings and endings is a breathtaking alternative to a single, linear history. Some cosmological models propose a cyclic cosmos, one that breathes in an endless rhythm of expansion and contraction. In this vision, our Big Bang was not the absolute start, but merely the latest in an infinite series of cosmic rebirths. a great crunch would follow the current expansion, collapsing everything back into a hot, dense seed, only for another bang to ignite a new universe from the ashes of the old. This elegant picture of eternal return, however, collides head-on with one of physics's most unyielding laws. The second law of thermodynamics dictates that entropy, the measure of disorder, must always increase. Think of it like a deck of cards. With each shuffle, the ordered sequence is lost and the disorder increases. In a cyclic universe, each cycle would be like another shuffle, adding more and more disorder to the cosmic deck. After countless cycles, the universe would be a featureless, high-entropy soup, utterly incapable of forming the galaxies and stars necessary for a fresh start. So how could it possibly reset to the pristine, low-entropy state required for a new Big Bang? This is the profound entropy problem for a cyclic cosmos. How can the universe wind its spring back up after it has completely run down? One proposed solution involves the mysterious nature of dark energy. Perhaps in the far future, dark energy drives such a violent acceleration that it dilutes all matter and energy to near nothingness, effectively erasing the universe's memory and resetting entropy to zero. Another idea, rooted in string theory, suggests that our three-dimensional universe is a membrane or brain floating in a higher dimensional space. Collisions between these brains could generate the energy for a new Big Bang, with the collision itself scrubbing the slate clean, dissipating the old entropy into the bulk of higher dimensions. Yet these are highly speculative, pushing the boundaries of known physics. The paradox forces us to confront the very origin of the arrow of time. If the universe truly cycles, then the low entropy of our beginning was not a singular miracle, but the result of a physical process we do not yet understand. The search for a self-consistent model of eternal return is a quest to reconcile the relentless march of time with the poetic idea of cosmic rebirth, a challenge that ultimately leads us to question where the laws of physics themselves even came from. The very laws of physics themselves form the ultimate paradox. We use these rules to explain the cosmos, from the spin of an electron to the birth of a galaxy, but we are left with a deeper, more fundamental mystery. Why do these laws have the specific, precise form that they do? Are they the only possible set of rules that could logically exist, a necessary truth written into the fabric of reality? Or are they merely contingent, one random selection from a near-infinite menu of possible universes, most of which would be dark, lifeless, and chaotic? This question pushes science to its absolute limits, blurring into the domain of philosophy. Some of our most advanced theories, like string theory, propose a staggering answer known as the landscape. In this view, the fundamental constants of nature, like the strength of gravity or the mass of an electron, are not fixed. They are the accidental outcomes of how extra dimensions of space curl up and settle into a stable state, a process that could have happened in countless different ways. Each stable configuration represents a different vacuum, a different universe with its own unique physical laws. In this vast cosmic landscape, most universes are stillborn, with constants too hostile for any form of complexity to arise. We, quite simply, could not exist in any of them. This is where the anthropic principle returns with profound force. We observe a universe with carbon, water, and stable stars, not because these laws are special or designed, but because we are here to observe them. Our existence as conscious observers acts as a filter, selecting for the rare, habitable corners of the multiverse. This logic can feel deeply unsatisfying, like an explanation that explains nothing. It leads us to the precipice of the ultimate why question. Why is there something rather than nothing? And why does that something obey elegant, mathematical rules that our minds can comprehend? The quest for a final theory, a single equation from which all of physics flows, is the drive to answer this meta-paradox. We seek a reason for the laws, a necessity that would make our universe the only one possible. Yet, even if we found such a theory, we would still be left wondering why that particular equation describes reality at all. This contemplation of the universe's deepest rules forces us to look not just inward, but outward, to the very edge of everything we can possibly see. Our cosmic horizon is a wall of time, not space. The furthest light we can possibly see is the cosmic microwave background, a fading glow from when the universe first became transparent. This shell of ancient radiation marks the ultimate boundary of our vision. We can never know what lies beyond it, not because it is too far, but because the light from those more distant regions has not had enough time to reach us in the nearly 14 billion years since the cosmos began. This creates a profound paradox. Everything we know about cosmology, from the Big Bang to dark energy, is inferred entirely from this finite, observable sphere. Yet the universe itself is almost certainly much, much larger than this pocket we call home. Inflationary theory suggests that the entire cosmos is staggeringly vast, perhaps even infinite, with our observable universe being just one tiny bubble in an endless froth. We are like a sailor in the middle of an ocean, able to see only to the horizon in every direction. We can measure the water, the weather, and the waves within our view, but the true scale and nature of the entire ocean remain a mystery. Our entire scientific understanding of the cosmos is based on the fundamental assumption that our local sample is representative of the whole. We assume the laws of physics are the same everywhere and that the universe is homogeneous on the largest scales. But what if it is not? What if, beyond our horizon, the universe is radically different? The strength of gravity could be stronger, the density of matter could be higher, or the very number of spatial dimensions could change. This limitation forces cosmologists to work with an eternal caveat. Any statement about the entire universe is really a statement about the part we can see. This uncertainty directly affects our predictions for the ultimate fate of everything. Is the universe truly destined for a cold, dark expansion, or could a vast, unseen structure beyond our horizon pull everything back together? The answers to these questions are hidden from us, locked behind a curtain we can never part. This fundamental limit to human exploration is humbling. It means we are forever confined to a single chapter of a story whose full length we can only guess. The paradox of our cosmic horizon forces us to confront the possibility that our entire reality is just a local neighborhood, one island in a possibly infinite archipelago of universes within the grand multiverse. This contemplation of the very largest scales and our inability to see them finds a strange and troubling echo in the physics of the very small. Gravity feels utterly dominant in our daily lives, holding planets in orbit and our feet firmly on the ground. Yet on the microscopic scale, it is the weakest force by an almost laughable margin. A simple fridge magnet lifting a paperclip against the gravitational pull of the entire Earth demonstrates this shocking imbalance. The electromagnetic force in that tiny magnet effortlessly overpowers the gravity of a world. This is the hierarchy problem, a paradox that asks why gravity is so unimaginably feeble compared to the other fundamental forces. The difference in strength is not a small factor. It is a factor of 1 followed by 36 zeros. To grasp that number, imagine the entire visible universe. Now compare its scale to a single atom. The difference in strength between gravity and the other forces is even more extreme than that. This is not a minor curiosity. It points to a deep, unnatural fine-tuning within the standard model of particle physics. The core of the problem lies with the Higgs boson, the particle that gives all others their mass. The predicted mass of the Higgs should be driven to an astronomically high value by its quantum interactions with every other particle. To keep the Higgs mass at the low value we actually observe requires a cancellation of these quantum effects so precise it seems like a cosmic miracle. It is as if two opposing numbers, each larger than the entire universe, were balanced against each other to produce a result of one. Without some new physical principle to explain this, it appears that the universe has been arbitrarily fine-tuned, an answer that leaves physicists deeply unsettled. This paradox is a powerful motivation for theories that go beyond the standard model. Supersymmetry, for instance, proposes that every known particle has a heavier superpartner. The quantum contributions from these partner particles would naturally cancel out the problematic effects, stabilizing the Higgs mass and explaining the hierarchy without any miraculous fine-tuning. So far, however, our most powerful tool, the Large Hadron Collider, has not found any direct evidence for these superpartners. Another radical idea involves extra dimensions of space. Perhaps gravity is not weak at all, but only appears that way to us. In these theories, the fundamental strength of gravity is comparable to the other forces, but it is diluted because it can propagate through these hidden, extra-dimensional realms. We, trapped in our three-dimensional world, only experience a faint shadow of gravity's true power. The hierarchy problem is a glaring crack in our understanding, a sign that the standard model is incomplete. It drives the quest for new physics at energy frontiers, pushing our colliders to greater heights in the hope of glimpsing the particles or forces that naturally resolve this cosmic imbalance. This desperate search for a deeper explanation for gravity's weakness inevitably leads us to ask if gravity can even be described by quantum rules at all. Our struggle to explain gravity's profound weakness stems from a deeper schism in physics. Two magnificent theories govern our universe, but they speak completely different languages. General relativity paints gravity as the elegant curvature of spacetime, a cosmic landscape where planets and stars roll along like marbles on a stretched sheet. It is a theory of the very large, of smooth, continuous geometry. Quantum mechanics, in stark contrast, describes a frantic, probabilistic world of tiny particles and fields. Here, reality is grainy, uncertain, and defined by sudden jumps and interactions. For a century, these two frameworks have remained stubbornly separate, refusing to merge into a single, coherent picture. This is the monumental problem of quantum gravity, the final and greatest paradox in our quest to understand the cosmos. The conflict becomes catastrophic in the most extreme environments imaginable. At the heart of a black hole, or at the very moment of the Big Bang, the universe was compressed into an infinitesimal point of infinite density, a singularity. Here, the warping of spacetime described by general relativity becomes so severe that it must somehow blend with the fuzzy quantum nature of matter and energy. Our current equations simply break down, producing nonsensical infinities. It is as if we have two perfect maps, one for navigating continents and another for exploring individual atoms, but no map at all for a city that is both a continent and an atom at the same time. To resolve this, physicists have proposed breathtakingly ambitious theories. String theory suggests that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. The different vibrations of these strings give rise to every particle and force, including the graviton, the hypothetical quantum carrier of gravity. In this view, spacetime itself has extra, hidden dimensions curled up at these microscopic scales. Loop quantum gravity takes a different path, proposing that space itself is not smooth and continuous, but is woven from a fabric of finite, tiny loops. Space and time are quantized, emerging from a network of these discrete connections, much like a digital photograph emerges from individual pixels. The challenge is that these ideas currently exist in a realm beyond direct experimental proof. The energy levels required to test them are far beyond anything our particle colliders can achieve. We are like architects who have designed two different, beautiful blueprints for a unified castle, but we lack the tools to build it and see which one stands. This is not merely an academic exercise. A successful theory of quantum gravity would answer the most profound questions we can ask. What truly happened at the instant of the Big Bang? What is the ultimate fate of a black hole and the information it swallows? It would complete the revolution that began with Einstein, giving us a single, universal language to describe everything from the birth of the cosmos to the dance of subatomic particles. The quest for this final unification forces us to the very edge of scientific explanation, to a paradox that questions the power of reason itself. The human mind has unraveled paradoxes from black holes to the quantum vacuum, yet our greatest challenge may be the mind itself. This is the meta-paradox of explanation, a question that looms over our entire cosmic quest. Can science ultimately explain everything, or are there fundamental walls we can never scale? The brilliant logician Kurt Gödel delivered a shocking answer from the heart of mathematics itself. His incompleteness theorems proved that within any sufficiently complex mathematical system, there will always be true statements that cannot be proven using the rules of that system. The system cannot validate its own consistency from within. It is like a rulebook that cannot confirm whether it is free of contradictions, no matter how thoroughly you read it. If this is true for the abstract world of numbers, what does it imply for the physical cosmos? Our entire scientific enterprise is built on a mathematical foundation. We use the language of equations to describe the laws of physics. If mathematics contains inherent, unprovable truths, then the universe it describes might also contain phenomena that are, in principle, unknowable to us. We are part of the system we are trying to explain. Our consciousness, the very instrument we use to probe reality, is an emergent property of the universe's physical laws. Can a process fully comprehend the system that gave it birth? This leads to profound questions about the role of the observer. In quantum mechanics, the act of observation seems to collapse a wave function, intertwining the observer with the outcome. Is consciousness not just a passive receiver of information, but an active participant in shaping reality? If so, a truly objective, final theory might be a mirage, forever receding as we approach it. Some physicists hold an unshakable faith in the power of science. They argue that for every barrier, a new paradigm will emerge, granting us deeper access to reality's core. Others believe we will eventually hit a fundamental limit, a cosmic horizon of the mind. We may be like deep-sea fish, capable of exploring our dark ocean, but forever incapable of formulating a concept of the sun. This is not a failure, but a call for humility. The eternal presence of mystery does not diminish knowledge, it frames it. Our journey through these 32 paradoxes reveals a cosmos that is not a puzzle to be solved, but a mystery to be engaged. Each contradiction we unravel does not lead to a final answer, but to a deeper, more beautiful question. The universe's grandeur lies not only in what we can explain, but in its boundless capacity to inspire wonder and remind us of our unique, curious place within it. Our voyage through these 32 unraveled paradoxes has revealed a cosmos far stranger and more dynamic than we ever imagined. We began with a simple question about a dark night sky and journeyed to the precipice of quantum gravity, discovering at every turn that our universe is not merely a collection of objects, but a tapestry of profound and interconnected mysteries. Each paradox, from the timeless twin to the silent cosmos, has acted as a powerful catalyst. They are not failures of knowledge, but milestones of progress, each resolution forcing science to evolve, to abandon comfortable assumptions, and to deepen its understanding of reality. Every answer we have found has not closed a book, but has instead opened a new and thrilling chapter in cosmology and physics, revealing deeper questions hidden just beneath the surface. This journey underscores the true beauty of scientific inquiry, the relentless human pursuit of truth in the face of the vast and humbling unknown. Let these mysteries ignite your own curiosity. The universe is not a finished story, but a living, breathing puzzle of infinite layers, and it is waiting to share its next great secret with anyone who dares to look up at the stars and wonder. Thank you for exploring the very edges of understanding.